Hello and welcome to this FMSPW SUMP session on the topic of indices and logarithms. I hope that some of the materials within the presentation will prove useful to you. As this presentation is concerned with work on indices and logarithms, it is probably worthwhile reminding ourselves of the basic laws of indices, which are shown below. Now moving on to consider logarithms. As described in the written note, logarithms allow us to write index relationships slightly differently. Starting with the basic definition of a logarithm, it is worth noting that the value of a in the notation used is known as the base of the logarithm. And the highlighted example hopefully serves to illustrate the connection between logarithms and indices. And finally, we have the laws of logarithms, which really are just restatements of the laws of indices from the previous slide. We will next consider some introductory examples involving indices and logarithms. In this initial example, we are asked to put some values into order of size, and each of the expressions involves the use of indices. You may wish to pause the video at this point in order to have a go at the question, as suggested. We will consider each of the values in turn. 81 to the power a quarter is the same as the fourth root of 81, which is 3. This is since 3 to the power 4 is 81. The next value of 2 to the 3 over 2 can be considered as 2 to the power half raised to the power 3, which in fact is the square root of 2, all cubed, which can be simplified by writing it as root 2 times root 2 times root 2 to give us 2 root 2. And this is clearly less than 3. The next value is 1000 to the power 1/6, which we can consider to be 1000 to the power 1/3 multiplied by 1/2, which we can then consider to be 1000 to the power 1/3 raised to the power 1/2 from the laws of indices. And this is the cubed root of 1000, all square rooted, which on simplification becomes the square root of 10, and this is clearly greater than 3. And so finally we put the values into ascending order. This second question is another example involving indices, and again you may choose to pause the video at this point before moving on. In this question, we will begin by simplifying the left-hand side of the equation using the laws of indices. This then becomes 10 to the power 6n. The long number on the right-hand side is clearly a power of 10, and by counting zeros we see it as 10 to the 24. Using these, the equation becomes 10 to the 6n equals 10 to the 24, so 6n is 24, and this gives us a final solution of n equals 4. This next example clearly involves the use of logarithms. Here you were given a number of statements involving logarithms and asked to decide whether in fact each statement is true or false. Again, you may choose to pause the video at this point before moving on to see the solutions to this question. Here we will consider each statement in turn. Statement A says, in the language of indices, that 2 to the power 4 is equal to 8. This is clearly false. The first part of B states that 10 cubed is equal to x, and so clearly x is 1000. Therefore, B is true. In part C, If we consider the left-hand side of the given equation, we can simplify this using the subtraction law for logarithms. This gives us log of x to the 99 over x to the 98, which in fact is the log of x. And so this is clearly true. In part D, we can simplify the left-hand side of the expression using the addition law for logarithms to get the log of x squared multiplied by x to the 4, which is in fact the log of x to the power 6, which is false. In part E, if we take the left-hand side, we can simplify this using the index law for logarithms and get the log of a to the y raised to the power of x, which is the same as the log of a to the power of x multiplied by y, or yx. This can in turn be considered to be the log of a to the power x raised to the power of y, which again, using the index law for logarithms, can be written as y multiplied by log of a to the x, and so is true. In part F, we can consider minus log x as minus 1 multiplied by log of x, which then, using the minus 1 as a power, we get the log of x to the minus 1, which is the log of 1 over x, and so this is clearly true. As the note explains, the main exercises that follow contain questions which we would strongly recommend you attempt by pausing the video prior to seeing the solutions for each one. As the little note at the bottom says, good luck with them. Pressing pause at this point will give you a chance to pause the video, think about the question and to give it a try. Here we will consider each value in turn. The square root of 2 to the power 4 on expansion becomes the square root of 2 squared multiplied by the square root of 2 squared, which in fact is 2 times 2 and so is worth 4. Log base 2 of 8 is 3, since 2 cubed is equal to 8. Log base 4 of 2 to the power 4 is in fact log base 4 of 16, and 16 is 4 to the power of 2, and so this is worth 2. The log base 2 of 2 is 1. This is due to the fact that 2 to the power of 1 is equal to 2. And looking carefully at the values found, we can put these values into order as shown. When you are ready, you should pause this video and give the question a go. Firstly, we need to note that the given values are in ascending order. Also, x to the power of 0 is 1. Since this is the largest value, we may think about values of x lying between 0 and 1. However, when we do this, this implies that, for example, the x squared would be less than x, and this is not true. If we consider x to be less than minus 1, this would imply that x cubed is less than x. Again, this causes a contradiction. Next, we consider values of x in the region from minus 1 to 0. An example of this would be using x equals minus a half, and this would in fact give the values shown, which are acceptable. And so it only remains to decide where in this list minus x to the minus 1 would fit. And using minus a half, we can see the value 2, and so this number is in fact the largest and goes in the list after x to the power 0. Again, press pause when ready and give it a try. This is personal preference, but I would prefer to express the given decimals as fractions in order to proceed with this question. Considering each of the given values in turn, we see that 0.1 to the power minus 2 is 1 over 1/10 squared, which is in fact worth 100. 0.5 to the minus 1 is 1 over 0.5, which is in fact worth 2. 0.5 to the power 1 is simply a half, and 0.1 squared is a 10th squared, which is 1 over 100. It only remains to add these fractions, which in fact gives us a total of 102.51. expressing the answer as a decimal, since this is what was given in the question. As the little message suggests, you probably know how to proceed from here. Since the given solution is a product of prime factors, we will prime factorise each of the given values. Since 6 is 2 times 3, we have that root 6 is 2 to the half times 3 to the half. We will consider each of the given square roots in a similar manner as shown. Root 12 is 2 to the 1 times 3 to the half. Root 18 is 2 to the half times 3 to the 1. 24 is 2 cubed multiplied by 3, and so root 24 is 2 to the 3 over 2 times 3 to the half. 30 is 2 times 3 times 5, so root 30 is 2 to the half times 3 to the half times 5 to the half. The square root of 36 should be immediately recognisable as 2 times 3, or 2 to the 1 times 3 to the 1 to keep the notation consistent. And finally, since 42 is 2 times 3 times 7, we have that root 42 is 2 to the half times 3 to the half times 7 to the half. Combining all of these results into a single product and using the additive rule for the multiplication of indices, we get, and when we simplify this, we get, and so the sum of A plus B plus C plus D is 11 as shown. Once again, press pause when you are ready and give it a try. This particular problem can be dealt with in a manner similar to the last example. However, it is worth noting that all of the given values are in fact powers of 2. We will now use each of these powers of 2 within the given roots. The cubed root of 4 is 2 to the power 2/3. The fourth root of 8 is 2 to the power 3/4. The fifth root of 16 is 2 to the power 4/5. And the sixth root of 32 is 2 to the power 5/6. Hence, the given product of the roots is as shown, which we can simplify using the addition law of powers to give us 2 to the power 61/20, which is 2 to the power 3 1/20, which using the laws of indices can be written as 2 to the power 3 multiplied by 2 to the power 1/20. And writing this in the root notation, which is given in the question, gives us that x must equal 20. As is implied by the additional note on this question, it would be quite simple to just evaluate the values on a calculator. However, that is not really the purpose of this work. As the little note below says, you know what to do. Good luck. First of all, notice in this question, we are not required to find the value of either of the given values. We simply need to decide which of the two values is the larger. We can take advantage of this fact during our solution. If we consider the fraction 5 to the power 6 over 6 to the power 5, we simply need to decide whether this fraction is greater than 1 or less than 1. On expansion of these values, we get, and we can now consider this to be expressed as shown. And since 25 over 6 is clearly more than 4, this expression is more than 5 over 6 to the power 4 times 4. We will next consider 5 over 6 to the power 4 multiplied by 4. This we can consider to be 5 over 6 to the power 3 multiplied by another 5 over 6 multiplied by 4, which is 5 over 6 cubed multiplied by 20 over 6, which is clearly worth more than 5 over 6 cubed times 3. We will next consider 5 over 6 cubed multiplied by 3. which we can consider as 5 over 6 squared multiplied by 5 over 6 multiplied by 3, which is the same as 5 over 6 squared multiplied by 15 over 6. And this is clearly more than 5 over 6 squared multiplied by 2. The value of this is now quite simple to calculate as 25 over 36 multiplied by 2, which is 50 over 36, and this is clearly greater than 1. Therefore, it follows that 5 to the power 6 must in fact be greater than 6 to the power 5. Again, in your own time, when you are ready, you know what to do. In this question, for convenience, we will let the two given logarithms be denoted by x and y respectively. Expressing these expressions in terms of indices rather than logarithms gives us that a to the x equals 4 and a to the y is equal to 2. It is clear that 4 is greater than 2, and so we can deduce that x must be greater than y. And so in this case we deduce that log of 4 must be greater than log of 2. Those of you that are particularly observant may notice that I left the letter T out. I did know how to spell highest, and I hope you didn't mind me handwriting the letter T on the end of the word. When you are ready, I am sure you know what to do. In this question, we will consider the value of each of the terms in turn. Square root of 2 to the power 4 can be considered as the square root of 2 squared multiplied by the square root of 2 squared, which is 2 times 2, which is 4. The log of 8 in base 2 is 3. This is since 2 to the power 3 is equal to 8. Since 2 to the power 4 is 16, this third logarithm can be regarded as log base 4 of 16. And this in fact is 2. This is true since 4 to the power of 2 is equal to 16. And finally, in base 2, the logarithm of 2 is 1. This is since 2 to the power of 1 is equal to 2. And now sorting these into ascending order of size, we have the following. Not many to go now. When you are ready, you know again how to proceed. In considering the value of this expression, we should first of all begin with 8 to the power 3. And since we wish to express this as a logarithm of base 2, then we should consider this using powers of 2. And so we deduce that 8 cubed is in fact the same as 2 to the power 9. And so it follows that log base 2 of 8 cubed is the same as log base 2 of 2 to the power 9, which is in fact 9. If we now use this fact within the given initial expression, we can see that we are required to find the value of log base 3 of 9. And since 9 is 3 squared, this is simply 2. Well done if you have reached this point. This is the final one in the exercise, and so good luck with it. Again, I'm sure you know what to do. The first steps we will take in solving this equation are to manipulate the left-hand side of the equation using the basic laws of logarithms. The first term can be simplified as shown. And so the given equation now becomes, and we can further simplify the left-hand side of this equation by using the subtraction law for logarithms. Now, since we're using logarithms of base 2, it is worth noting that it is the log of 4 that is worth 2, since 2 squared is equal to 4. And using this, the given equation now becomes x over 1 minus x equals 4. And solving this equation, we can see that in fact the value of x must be 4/5. I'm sorry if you felt a little bit misled with the last question, as it wasn't really the final question, as we have chosen to add an additional question which comes from the mathematics admission test. Again, press pause, give it a go, and good luck with this one, and I promise this is the last question. In this question, we need to consider which of the given expressions has the smallest value. In order to do this, we will consider the value of each expression in turn. The first expression is log base 10 of pi. Initially, we should note that the value pi is smaller than 10, and in fact, pi is a reasonable approximation for the square root of 10. And so pi can be written approximately as 10 to the power half. This means that log 10 of pi may be written approximately as log 10 of 10 to the power half, which in fact is equal to 1/2. We will next consider the value square root of log 10 of pi squared. And using the laws of logarithms, we can see that this is the same as the square root of 2 log 10 of pi. And combining this with the above result, we get an approximate value of the square root of 2 times 1/2, which is 1. We next consider the value 1 over log 10 of pi all cubed, and using the value of log 10 of pi from the initial expression, we can see that this is approximately 1 over 1/2 all cubed, which is approximately worth 8. And considering the final given value, 1 over log 10 of root pi, we can initially manipulate this using the laws of logarithms to get 1 over 1/2 log 10 of pi, as shown, and this then can be approximated using the first value to give 1 over 1/4, which is approximately 4. And now, considering all of these results, we can see that the smallest value, which is the one we were required to choose, is in fact the first value, log base 10 of pi. Thanks for your time in watching this presentation, and as the message says, I hope that you will have found something within this presentation useful to you. Thanks again, goodbye and good luck.